thanks to your local cable company. You're watching the Learning Channel.
Imagine a universe infinitely small, then an explosion of incredible fury, what we call the Big Bang. Elementary particles, the building blocks of matter, hurtle through space at incredible speeds. Awash in a sea of intense heat, they are unable to bind together. But as the newly born universe expands, it begins to cool. A second after the explosion, new particles form. Protons and neutrons, the ingredients of an atom, begin to appear. After 3 minutes, conditions are ripe for the manufacture of primeval hydrogen and helium. An hour after the Big Bang, the newly created elements will fill every corner of the universe. Today, 15 billion years later, as we look around us, we see many elements besides hydrogen and helium. The Earth, the atmosphere, and all living things are also composed of heavier elements, such as carbon, oxygen, iron, magnesium, and potassium, to name a few.
The trillions of tons of heavy elements making up the ground under our feet makes us feel these elements are everywhere. But the planet-bound view is distorted when we consider how exceptionally rare the substances composing dirt are in all the universe. When we look at the whole cosmos, we see that hydrogen and helium still dominate. Compared with these two primal substances, the combined totals of all the other elements are less than 1% of the total mass. So where did all these rare elements come from? We now understand that they are a gift of the stars. Our planet, we ourselves, are all composed of a fantastic substance indeed. We are all made of stardust.
But where did stars come from in the first place? How did the smoothly expanding universe give birth to these dense, brilliant balls of gas? For a while, the stars and their galactic homes defied explanation in the Big Bang scenario. But recently, we moved a little closer to unraveling the mystery. In 1989, NASA launched a satellite called COBE to explore an unusual phenomenon called cosmic background radiation, a faint but all-pervasive noise emanating from deep space. Because it seems to come from everywhere, scientists believe it's a remnant of the Big Bang before the universe broke up into galaxies. If so, measurements taken by the satellite may give us new information about how the early universe was formed.
As far as we know, the universe began with what's called the Big Bang, a massive explosion which created essentially everything that we know today in the universe. And the universe has since expanded and continues to expand today. The structures which we see in the universe are remnants, relics of the original explosion, and the developments that have taken place since then have given us an idea of how that original explosion took place and what has happened since then.
These gigantic and ancient structures across the sky tell us that some parts of the very early universe were denser than others. The denser areas, influenced by gravity, drew in upon themselves and became the birthplaces of galaxies and stars. As a protostar grows, it begins to collapse under its own weight. As it contracts, hydrogen atoms begin to collide faster and faster, causing the gas to heat up. Eventually, it becomes so hot that the atoms no longer bounce off of each other. Instead, they fuse to form helium. The energy produced by the fusion of hydrogen atoms is enormous. We have learned how to fuse hydrogen to form helium. The result? The hydrogen bomb.
As with the explosion of the H-bomb, from stars we see immense heat and light. Each star releases the energy equal to thousands of H-bombs every second. Fortunately, a lot of energy comes from very little mass, so there's plenty of hydrogen to keep some stars shining for billions of years.
But no matter what mass a star has, its supply of hydrogen fuel eventually runs low. When that happens, it begins to die.
The death stage, or the last stage in the life cycle of a star, is governed principally by the amount of mass that star has to deal with. If it's a very massive star, much more massive than our sun, say 100 times more massive than our sun, or 50 times more massive than our sun, we expect that in the collapsed state it will produce what is called a black hole. Objects, say more intermediate in mass, say maybe just 10 solar masses, would collapse to form objects called neutron stars. And then garden variety objects like our sun and smaller masses would collapse to form white dwarfs. So we think that the last stage in the development of all stars, depending on their mass, would be either a white dwarf, a neutron star, or a black hole.
We'll return to the Practical Guide to the Universe on the Learning Channel. We now return to the Practical Guide to the Universe on the Learning Channel. A star lives out its life on the verge of being crushed by its own weight. Gravity constantly pulls inward, attempting to crush the star into the smallest space possible. Only the outward pressure, due to the heat in the star's fiery furnace, prevents its collapse. The buildup of helium ash pushes hydrogen away from the core where fusion can happen. Energy production drops and the star reaches a stage when not enough heat is produced to support the star against its gravity. The star contracts until the temperatures and pressures are high enough to cause the helium to fuse into oxygen, and oxygen to fuse into carbon. This additional fusion gives the star a short reprieve from destruction.
Now, you might suspect that all heavy elements are simply made in successive stages, similar to what has happened with helium, where with additional heat and pressure, the element changes from being an ash to become a fuel. And it does work that way for a time, but it's not quite that simple. Size makes a difference in how long a star will shine.
Surprisingly, less massive stars last the longest. More massive stars generate much higher temperatures and pressures in their cores. They burn more vigorously and use up their fuel in a few million years. The smallest stars burn very slowly and can last, in theory, nearly 1 trillion years. Our nearest star, the Sun, is 5 billion years old. Because a star fueled by hydrogen grows hotter throughout its life, the Sun, when it was first formed, produced about 70% as much energy as it does today. This slow and gradual increase in the temperature helped life get a foothold on the Earth. By the time it has converted almost all of its hydrogen to helium, in about 5 billion more years, the Sun will shine twice as brightly as it does today. When the hydrogen finally runs out, our Sun will change drastically. It will become what is known as a red giant. It will fade to red and swell, engulfing Mercury and Venus. Earth's oceans will boil, and the land will bake. Now fueled by helium, the Sun will begin a brief second life. It will stabilize, shrink, and burn for several million years more until the supply of helium is also exhausted.
For stars the size of our Sun, there is not enough gravity to produce the heat and density necessary to ignite any large-scale burning of oxygen and carbon. These waste products of helium fusion simply accumulate in the core.
Even so, some heavy elements are made. Deep inside stars, small amounts of them accumulate, but much more slowly than the primary ash products like helium, carbon, and oxygen. When helium fuel runs low, the star expands again. In the second red giant stage, convection currents carry heat to the surface and disperse these heavier elements throughout the star. For a star like our sun, its great glory is this last massive appearance. The end is near, and the star begins to shed much of its bulk. Shock waves rising from its turbulent interior blast the star's surface gases into space, where they condense into solid grains called dust. This dust is then blown further outward from the dying star by a phenomenon known as the stellar wind. Around the shrinking star, a cloud of glowing gas and dust forms. This is a signal that the star has reached the end of its life. Having blown off the outer atmosphere, what remains is a small, naked core called a white dwarf. Now only a little larger than Earth, the dwarf still contains nearly half the mass of the sun. Ironically, a white dwarf burns brighter than it did as a normal star, but it emits less light because of its small size. Over billions of years, it will slowly cool until it finally becomes a black, cold cinder. Our sun will be dead. But large stars, 10 or 20 times more massive than the sun, follow a different path. Their lives are much shorter, lasting only millions of years, but they can burn more kinds of fuels. The immense gravitational crunch of a very large star can continue to fuse heavier elements even after the hydrogen and helium start to run out. It begins to burn in layers, like an onion. The outer layer fuses whatever hydrogen is left into helium. The next layer fuses helium into carbon, and the next carbon to oxygen, and so on, each layer fusing heavier and heavier elements until at the core, silicon and sulfur begin to fuse. The product of the silicon and sulfur fusion is iron. Iron is the end of the road for the star, because iron cannot be fused to produce more energy.
When the iron core is about 1.5 times more massive than our sun, no more energy is produced from fusion in the core. The core size is about as big as the Earth. For this star, the end comes quickly.
And catastrophically. The iron core falls in upon itself. Its diameter shrinks from thousands of miles to 100 miles in 1/10 of a second. The falling material crashes into itself at the center, generating a rebound shock wave. The star is about to become a supernova. We'll return to the Practical Guide to the Universe on the Learning Channel. We now return to the Practical Guide to the Universe on the Learning Channel.
In the collapse, the star expends unbelievable energy. Our sun's energy output is nothing compared to such a collapse. If this energy was released as light, it would outshine the combined light of all the stars in the universe.
But most of that energy, better than 98%, comes out as neutrinos. Neutrinos are elusive particles that only rarely react with other matter. To stop one, a lead shield would have to be 8 trillion miles thick. Normally, neutrinos leave a star's core unhindered. They zip through tons of stellar mass into space as if there were nothing in the way. But in a supernova, conditions are not normal. The compression in the shock wave is so great that even neutrinos have to struggle to get out. A tiny fraction of them interact with the surrounding matter, adding to the awesome power of the event. With a force unequaled in the universe, the star explodes in a miniature Big Bang. Imagine billions of suns switching on for an instant inside a single exploding star, blowing away all of its outer layers. As the shock wave passes up through the layers of the star, it causes nuclear fusion of all the known elements. Material closest to the center becomes the heaviest elements, such as plutonium and uranium. Those farther out form lead, gold, silver, and platinum. All the complex elements present in the universe and in our own bodies were created in the heart of an exploding sun. In the universe, the intense light of a supernova travels outwards, announcing the violent death of a star.
The remaining core of the star that's left behind by a supernova is called a neutron star. It's called that because it's mostly made of neutrons rather than the protons and electrons that make up most of the material in our world. An extremely dense object, perhaps only 10 miles across and yet having a mass greater than that of our sun, means that if you had a sugar cube made of neutron star material and brought it to the surface of the Earth, it would weigh something on the order of 300 million tons.
A stellar explosion ejects all the elements of the periodic table into space. There, they will become the stuff of other stars, planets, and even people.
This is a description of what is called a Type 2 supernova. There is also a Type 1, which is even more rare and more violent. This other kind of supernova is not caused by a big star collapsing. Rather, it is believed to be caused by two older stars similar to our sun after its red giant phase has passed.
In a Type 1 supernova, two white dwarf stars that orbit each other come together as they lose rotational energy. When they finally collide, their combined mass undergoes catastrophic gravitational collapse, forming a single structure called a black hole.
A black hole is a star that has collapsed on itself so that it got denser and denser as it fell together. And eventually, it's so dense, its gravity has become so powerful that it prevents anything from escaping. Even a ray of light, a beam of light can't escape from the star.
To get a better idea of how a black hole can stop light from escaping, consider this. A spaceship trying to leave the Earth has to reach a speed of about 25,000 miles an hour to be successful. Any slower, and it would be pulled back down to Earth by gravity. This is called escape velocity. If you were to squeeze the Earth down, the velocity needed to escape gravity would be higher because the surface of the Earth would be closer to the planet's center of gravity. Keep compressing the Earth until it is the size of a marble, and the escape velocity needed to leave the surface would be faster than the speed of light. The Earth would become a tiny black hole. There may well be several black holes in our galaxy, but as you can imagine, black holes are exceptionally hard to locate.
If you look at a black hole, you probably won't see anything, although if you're up close enough, not too close, and there's stars behind it in the background, you will see the pattern of stars just behind the black hole become distorted, may even look like a ring of light, just because the gravity of the black hole is so powerful it bends light rays that are passing by it. The way astronomers think they see black holes is by virtue of the effects of the powerful gravity of a black hole on its surroundings. There are what we think are gigantic black holes, the centers of galaxies, that seem to be pulling in swirling gas that falls towards them. As it falls towards them, it's getting packed closer and closer together. It's more viscous and denser, the gas becomes very hot, and it gives off X-rays and other forms of radiation, which we detect and we consider the likely signature of a black hole.
However many black holes there are, they are not the usual end of a star. Most stars in their deaths release the raw materials for other stars and planets.
Scientists believe that our own solar system is made up of the remnants of two such long-dead stars. Without supernova explosions, the Earth, and all life as we know it, would not exist.
In a way, it is strangely appropriate that the death of a star would seed the universe with the elements necessary for new life, much the same as a dead tree falls and fertilizes the soil for the renewal of the forest. It seems to be the way of the universe and ties the cycle of life we see upon the earth with the heavens above. For in the end, we are all made of stardust.
Some galaxies form neat spirals. Others are in total disarray. Find out why on the Practical Guide to the Universe, next from TLC.
When you look at the evening sky, away from bright city lights, you can appreciate what our ancestors saw every night of their lives. The sky is bursting with stars. Some are so bright they stand out like beacons. Others are dim. Most are crisp points of light, but some seem blurry.
These blurry stars are not individual stars at all. Some are, in reality, distant galaxies, many like our own Milky Way. If you live in a city with large amounts of street lighting as well as tall buildings, you can only see the brightest of stars in our own galaxy. Out here, when it's dark, you can actually see the band of the Milky Way, which has been called the backbone of night.
Even under the best conditions, the human eye is not sensitive enough to see more than a small portion of the stars in the sky. To really see what is out there, we need a telescope. If we can see 10 stars in a given patch of sky, a large telescope will reveal 100, 1,000, or possibly 10,000 more. Telescopes don't make the stars look any bigger. It just allows us to see the dimmer ones. But most are galaxies, great collections of billions of stars like our own Milky Way. They looked fuzzy because they were far away. But how far? No one knew. We now have a better understanding of the distances between us and the billions of galaxies in the universe. Galaxies that come in all shapes and sizes. By analyzing the color, brightness, and motion of stars, scientists built up an image of different types of galaxies, including our own Milky Way. It is a flattened disk about 100,000 light years in diameter. Surrounding it is a sphere of stars, a common feature called a galactic halo. The Milky Way is a spiral galaxy. Seen from above, it would look like a pinwheel rotating around a bulging central hub. Clusters of aging red giant stars give the hub its pale reddish color. Bright, hot stars in the spirals make them appear blue. But there are clusters of yellow stars like our own sun here and there as well. Our solar system is in one of the spiral arms, out about 2/3 of the way from the center. Mixed in with the stellar spirals are vast clouds of gas and dust. This matter was blown into space by dying stars and may collect again to form new stars. Some of these clouds are still spreading, away from an explosion that propelled them into space, leaving behind a remnant, the core of a once great star. A neutron star is one such remnant. Its core is composed almost entirely of a tiny particle of matter called a neutron. Neutron stars are so dense that 1 teaspoonful would weigh 50 billion tons on Earth. Some neutron stars are known by another name, pulsars. These stars get their name because of a regular pulsing beam of energy that they emit.
The fact that this big, slowly spinning star collapses to form the tiny neutron star makes it turn faster and faster. It also intensifies the magnetic field of the star. And what you find is, it's an observed fact, no one ever theorized these things would exist. What you find is that you have a pulsar, and that means the magnetic field is somehow channeling high-energy particles that produce radio waves that come out in 2 lighthouse beams to either side of the neutron star. And as the neutron star is turning, the pulsar is turning, these lighthouse beams sweep around space. And if they cross the Earth, then every time when a lighthouse beam comes by, it shines on our radio telescope for a fraction of a second, and we call it a pulse. And that's what a pulsar is.
Not all the clouds that we see in the Milky Way are spreading away from an exploding star. Some clouds are converging. They may become stellar nurseries, where new suns and new solar systems arise. Of course, what draws our attention when we look at the Milky Way is the abundance of stars. They come in various sizes and stages of development. There are young stars, middle-aged stars, and dying stars. Among the dying stars are a group called red giants. They're called giant for a good reason. A red giant is so big that if one replaced our sun, it would swallow Jupiter and Saturn. Others are called blue giants. These are young stars that are so bright and hot that the Earth would have to orbit well beyond Pluto to remain cool enough for life to continue. Yellow stars are numerous, and so are white dwarfs. Our sun has a lot in common with both. Right now, it is a yellow star, but it will become a white dwarf toward the end of its life. We'll return to the Practical Guide to the Universe on the Learning Channel. We now return to the Practical Guide to the Universe on the Learning Channel. Stars may develop singly, like our sun, or in systems of 2, 3, or even more. The more stars in a system, the more complex their interactions. For instance, 2 stars may orbit each other, and then the 2 together orbit a third. Imagine what life would be like on a planet in such a system with 2 or 3 suns in the sky. Darkness would be a rarity. The times of warmth and cold that we call summer and winter might not follow at annual patterns at all. Our world would be a much different place.
In binary or 2-star systems, one star as it gets old and becomes a red giant may lose mass to its companion. If its companion can't absorb it, a violent explosion may occur, what is called a supernova. The most curious object of all in the galaxy is an awesome phenomenon called a black hole. In the Cygnus X1 star system, matter from a visible star is spiraling towards an invisible object like water running out of a bathtub. The spiral is so hot, it produces X-rays, a telltale sign of a black hole.
Black holes are one of the strangest predictions of Einstein's theories. They're produced when a star collapses to the point where its gravity overpowers the strong nuclear force found in the nucleus of atoms. When that happens, the force of gravity pulls the star in upon itself until it disappears altogether. The matter of the star is gone. All that remains is its intense gravity. Even light can't escape from it. In fact, there may very well be a gigantic black hole at the center of our galaxy.
There are certainly evidence that there are black holes at the centers of some galaxies, and there's some indications even that there may be black holes at the centers of most galaxies. The evidence for a black hole at the center of our own galaxy is not extremely strong, but there's certainly possibilities. The fact that we see gamma radiation, particularly annihilation radiation, coming from matter-antimatter annihilation toward the center of our own galaxy, is an indication that something out there in that direction is producing vast quantities of antimatter, and a black hole seems to be a very good candidate for that sort of thing.
We tend to focus a lot on our galaxy, but there are billions just like it in the universe, and billions more that are different in structure. In the large view of cosmology, galaxies can be said to be very similar to atoms, because atoms can attract one another and form a molecule.
The same is true of stars and galaxies. Dust clouds attract each other and form stars and planets. These collect in large groups and form galaxies. When galaxies cluster together in space, they're called groups.
We don't know for sure why most galaxies are in groups, and a certain substantial fraction of galaxies are in the much more prominent formations we call clusters of galaxies. But the assumption is that whatever caused galaxies to form also caused groups and clusters of galaxies to form. That is, that there was something in that part of space, way back when, not long after the Big Bang, that caused stuff to accumulate in those regions of space and not in nearby regions. So that you have places where there are lots of galaxies, and then you have these gigantic voids where there appears to be almost nothing.
Our local group of galaxies is about 5 million light-years in diameter. It has around 20 galaxies, which represent several of the main galactic types. Only 2 others are spiral galaxies like our own. Most are spherical, and at least one is an elliptical galaxy. The nearest spiral galaxy is 2.3 million light-years away, the Andromeda Galaxy. Like ours, it is surrounded by groups of stars known as globular clusters. Our group of galaxies is part of a much larger group called a supercluster. It stretches an astonishing 100 million light-years in diameter. This particular supercluster contains our modest local group, the much larger Virgo cluster, and many other groups of galaxies. On an even larger scale, scientists have recently discovered that superclusters also form in groups. They are distributed throughout the universe in long, open filaments. In between are voids and pockets of nearly empty space. What could explain this apparent order? No one knows for sure, but the discovery has challenged our long-held theories about the origin of the universe.
In the 1920s, astronomer Edwin Hubble focused on the light emanating from distant galaxies. When seen through a prism, it broke down into a rainbow of colors called the spectrum. Through his observations, he found that the light from these galaxies was shifted towards the red end of the spectrum.
This shift, sometimes called the Doppler shift, is caused by movement of the light source toward or away from the observer. It's very important in astronomy for determining the movement of stars and galaxies.
Sound also exhibits the Doppler effect. If a car drives by and blows its horn, the pitch of the horn changes. It's higher as the car approaches and lower as the car leaves. The frequency of the sound wave determines the pitch. Light behaves the same way. The light from an object, such as a star or galaxy, shifts to a higher frequency if it is moving toward us. It shifts toward the blue end of the spectrum. If it is moving away, it shifts toward a lower frequency, or the red end of the spectrum. Hubble's discovery was startling. It not only meant that distant galaxies were moving away from us, they appeared to be flying away from each other.
Scientists quickly understood that if all of the galaxies are flying away from one another, then at some time in the past they must have been all in one place. And from there,
As far as we know, the universe began with what's called the Big Bang, a massive explosion which created essentially everything that we know today in the universe. And the universe has since expanded and continues to expand today. The structures which we see in the universe are relics of the original explosion, and the developments that have taken place since then have given us an idea of how that original explosion took place and what has happened since then.
We'll return to the Practical Guide to the Universe on the Learning Channel. We now return to the Practical Guide to the Universe on the Learning Channel. The original Big Bang theory did not account for clusters of superclusters and holes in the universe. If, after the initial explosion, conditions were the same everywhere, then the matter should be evenly distributed throughout the universe, but it's not. To close the gap between theory and reality, scientists now postulate that the density of matter in the early universe was not uniform. An instant after the Big Bang, it underwent a period of rapid expansion or inflation, which then amplified the non-uniformity, causing the density of matter to vary from place to place. In time, gravity would cause the denser regions of the universe to slow down and contract, and the formation of galaxies would begin.
it is still possible for astronomers to see the earlier stages of galactic creation because as telescopes grow more powerful and look further out into space, they're also looking further back in time. Now, this may sound odd, but let me give you an example.
In 1987, astronomers saw a supernova in one of the nebulae called the Magellanic Clouds. Although the event seemed to be happening in the present, in truth, it had happened over 150,000 years ago.
You see, the Magellanic Cloud is 150,000 light years away, so it takes light that long to get here for us to see it. And the same is true for the Andromeda Galaxy. We see it as it was 2.3 million years ago. Andromeda appears to us younger than it really is. When we look out billions of light years, we see galaxies in their formative stages as they appeared billions of years ago.
A galaxy evolves slowly compared to a human lifetime. What we see is only a snapshot, a single fleeting moment in its existence. But we can learn a lot from a moment. Looking out, we see galaxies in a wide variety of configurations. Edwin Hubble was the first to describe galaxies as ellipticals, spirals, and barred spirals. Later, astronomers added irregulars and peculiars. All these different kinds of galaxies are moving about in space, and sometimes, rarely, they collide.
This is not the most controversial subject, but it's still one where there's a lot of uncertainty, and it's only the last few years we're beginning to think we understand why different galaxies have their shapes. Probably most galaxies have actually started out as spiral galaxies, not too unlike our Milky Way. But then over billions of years of cosmic time, they collide with other galaxies. There's also evidence, including a lot of good evidence now from the Hubble Space Telescope, that the biggest elliptical galaxies we can see, the giant ellipticals that you often find at the center of a big cluster of galaxies, that these have clearly swallowed lots of other galaxies. And it looks like eventually, if you wait long enough, that most galaxies may end up either swallowing their friends and neighbors or being swallowed, like the fish in the sea.
There is so much space between the stars that they usually pass through each other successfully.
But where some of the larger suns come together, colossal impacts occur, which obliterate the stars and any matter near them. Our own galaxy is not in any such danger of a collision, but even in the cosmos, accidents do happen.
In the far distant future of our universe, however, galactic accidents may become the rule instead of the exception. You see, the universe may one day stop rushing apart and start rushing together again. The instruments that we use to look into deep space have told us much about the murky beginnings of time and space that we call the Big Bang. But they are also beginning to hint at our universe's ultimate end. It turns out that the Big Bang theory that best describes the cosmic architecture that we see today also predicts that the universe contains a certain amount of mass, and that amount of mass exerts just enough gravity to slow down, stop, and eventually reverse the outward expansion of the universe. If this theory turns out to be correct, our universe is one day headed for something called the Big Crunch. In the Big Crunch scenario, the universe will begin to back in on itself. In a reverse of the Big Bang, galaxies will race toward each other, collide, and ultimately compress into nothing. Time and space will come to an end.
The time for such an event would be billions, if not trillions of years in the future. We might wonder if our species will still be in existence to worry about it. Certainly we would be very different than we are today. Perhaps we would have discovered other universes we could flee to, or a way to rejuvenate the one we're in. These are fantastic notions, but we are an inventive race, and if we can learn to control our natures and channel our creative powers to constructive uses, we might be able to survive even the end of the universe.
They are swirling spheres of toxic gases, the giants of our solar system, the outer planets, on the Practical Guide to the Universe, next from TLC.
$4,500,000,000 years ago, a solar nebula takes form. It is a cloud of stardust, the stellar nursery, the mother of suns. At the cloud's center, gravity pulls in huge amounts of gas and dust, making the center hotter and denser. The nebula is on the verge of becoming the hydrogen fusion furnace we call a star. Away from the seething center, other forms mimic the giant cloud, taking on the size and shape of planets. Upon ignition, the young star casts out a continuous spray of fast-moving particles called the solar wind. Nearest its source, this gale strips away any gas or dust not tightly locked within the gravity of the forming protoplanets. The star's blast sweeps away what little atmosphere the closest planet has acquired. The next three, though small, manage to hang on to small envelopes of gas. The gases lost to the forming spheres that would one day become the inner planets flow outward towards other swirling masses. With its belly full of fuel, the new sun burns with great intensity, settling into its nuclear balance. The solar gale calms to a gentler wind. Further out from the sun, distance weakens the power of this solar wind. Particles move more slowly and are easily captured by the gravities of the large protoplanets. The first of these coalescing outer globes, a giant in the making, carries off most of these particles. Three other giants, huge compared to the inner planets but still dwarfed by the king, will catch the rest. The four huge protoplanets sweep out the space they travel through, hurting and consuming all dust and small bodies in their way. A new solar system is born. It is the future home of life forms who will someday gaze into the heavens from their small blue planet, third from the sun. The huge gas giants of the outer solar system will draw their attention, and they will wonder. They will wonder at the nature of these outer planets. Planets that have both the hottest and coldest temperatures of the solar system. Planets so gigantic that they could easily swallow the Earth. These are worlds where fire and ice live side by side, the residents of an ice-cold and burning hell. As we journey outward from the sun, we encounter all the various kinds of worlds that our solar system has to offer. Of these, the inner planets, Mercury, Venus, Earth, and Mars, are made up principally of rock with small atmospheres. We then pass the asteroid belt, which may be the remnant of a 10th planet that once circled the sun, but which now only serves as the demarcation line between the inner and outer planets of our solar system. Like the inner worlds, the outer planets have mythological names. Jupiter carries the name of the king of the Roman gods. Saturn takes its name from the god of time. Urania, a legendary astronomer, supplies the name of the planet Uranus. The sea god gives the planet Neptune its name, and the god of the underworld supplies the name Pluto. We'll return to the Practical Guide to the Universe on the Learning Channel. We now return to the Practical Guide to the Universe on the Learning Channel.
We can look at Jupiter in two ways, as a grand planet or as a pitiful stellar failure. When we say that Jupiter is a large planet, we are making an incredible understatement. Jupiter is absolutely enormous, by far the biggest planet of the solar system. It contains more mass than all of the other 8 planets combined.
Some people believe, based on a lot of data from Voyager and hopefully soon from Galileo, that Jupiter was almost a failed second sun, that we were almost a binary system, because Jupiter itself has a series of satellites, mini planets, which are organized like our solar system. They're organized as a function of heaviness or density, so that the more dense and heavy satellites of Jupiter in that system are nearest Jupiter, and then they go out progressively.
Though huge, Jupiter rotates rapidly. Its day lasts only about 10 hours. This quick spin may cause its violent atmospheric patterns. Dense clouds cover the planet just like Venus, but unlike Venus, Jupiter's clouds divide into beautiful and ever-changing bands of colors. Movements of particular clouds seem random and chaotic, but on the large scale, they produce features that persist for years, even centuries. The best known and most dramatic of these features is the Great Red Spot. The red spot is essentially a very large weather system like a hurricane or a typhoon, but with 3 significant differences. This storm has lasted at least 300 years. It's larger than the entire planet Earth, and its winds travel at 800 miles per hour. That's faster than the speed of sound. Such unearthly pressure and constant turbulence in the air make expeditions below the clouds impossibly hazardous. But it is doubtful we'll ever venture near these clouds anyway. You see, Jupiter gives off more intense radiation than anything we've ever encountered on Earth.
Jupiter's vast magnetic field acts like a particle accelerator so effectively that it produces almost 1 million rads of radiation. All the probes sent to Jupiter are devices made up of metal and inorganic compounds, so they can be designed to withstand this. However, we humans are a different story. It only takes 400 rads to kill a human being, instantly. Not a very bright picture for human exploration of the solar system's largest piece of real estate.
From a human perspective, Jupiter, the planet, is much less important than the moons it possesses. It has at least 16 known satellites. Probably dozens more await discovery. Some of these moons are bigger than some of the planets and provide us with many possibilities. If life outside the Earth is to be found in the solar system, the moons of Jupiter offer the most likely place. Europa fascinates us most because water covers its entire surface. Frozen water, yes, but water all the same. Its icy surface is as smooth as a billiard ball and crisscrossed by thousands of huge dark lines.
It has been theorized that the marks in the surface of Europa are really cracks in the ice caused by the upwelling of liquid water below the surface, much the same as is observed in the polar ice caps on Earth. So we suspect that sufficient warmth must be present on Europa at lower depths to sustain the kind of life forms that we have in our own oceans. With water, there is an improved possibility of developing habitable cities on the surface.
Io, the 3rd largest moon of Jupiter, is one of the reddest objects in the solar system thanks to its incredible volcanoes. Covered from pole to pole with huge volcanic eruptions, Io is clearly the most geologically active spot in the solar system. Jupiter's monster magnetic field plays havoc with Io, keeping its volcanoes erupting and its surface quaking. Like a cup of water boiling in a microwave, you can't see where the energy comes from, but the water boils all the same. Io shows the effects of invisible forces at work. Ganymede is the largest of Jupiter's moons. At 3,275 miles in diameter, it is bigger than the planets Mercury and Pluto. Callisto, the second largest of the Jovian moons, is composed primarily of rock and water ice. Galileo discovered these large moons with a telescope that he had built for himself for observation of the heavens, so in his honor, we call them the Galileans. They're visible on a dark night with only a modest pair of binoculars.
Saturn is the second largest planet in the solar system and the sixth planet from the sun. And despite its immense size, its mean density is less than that of water, which essentially means that if you could find an ocean large enough to drop Saturn into, the planet would actually float. Clearly, Saturn is made up of very light stuff indeed. It can't be much more than a giant gas bag mixture of hydrogen and helium.
Saturn's beautiful rings are its best-known feature. Galileo first caught sight of them back in 1610. At first, early observers thought the rings were part of the planet, solid shining disks connected to Saturn's surface. Some even argued that the beautiful rings were signs of intelligent life on the planet. Well, we now know exactly what the rings are. They're essentially small chunks of water ice that circle the planet upon a single orbital plane. Interestingly, Saturn gives off more heat than it receives from the sun. This energy seems to come from heat generated when the planet's formed, the same reason that Earth still has a molten core. Saturn has the most extensive satellite system of all the planets and possesses the second largest moon of all, the giant Titan. At over 3,100 miles in diameter, Titan, like Jupiter's Ganymede, is larger than the planets Mercury or Pluto. It also has a rather dense atmosphere, which is composed mainly of nitrogen. Until the Voyagers passed by Saturn and its moons, scientists thought Earth was the only planet in the solar system with an abundance of nitrogen in its atmosphere. Now we see that Titan not only has a nitrogen atmosphere, but it's 60% denser than our own, which is amazing because Titan is 1/3 the size of Earth. We'll return to the Practical Guide to the Universe on the Learning Channel. We now return to the Practical Guide to the Universe on the Learning Channel.
Jupiter and Saturn get a lot of attention because they're so big. But Uranus, as it turned out, proved more fascinating than astronomers on Earth had ever dreamed.
The most obvious oddity is that the planet appears to be tilted on its side. This means the sun shines more directly above its polar regions than its equator, as you can see from the position of the delicate rings. No one knows for certain why Uranus is tilted over 90 degrees on its axis. Some astronomers speculate that a planet-sized body crashed into Uranus early in its history, knocked it on its side, and formed all the moons and rings now circling around the planet. Uranus is about 4 times the size of Earth. It also appears that the 7th planet from the sun has a rocky core, about the size of Earth, and is surrounded by a sea of liquid water. This sea is totally unlike any earthly ocean. Its featureless surface covers more than 2.5 times the area of the entire Earth. The immense methane atmosphere and the intense gravity of the planet compress the water so much that it generates its own electrical fields. As a result, the water becomes superheated. Only the heavy atmosphere bearing down on this strange sea prevents it from boiling. It's an unexpectedly hot world to find orbiting so far from the sun. This electrically charged ocean produces 2 interesting Uranian features. First is a strange magnetic field that rotates on a highly irregular orbit about the planet. The magnetic field, in turn, creates the second feature. It is something scientists call electroglow. Uranus, as it orbits in dark space, has an eerie, nebulous glow of electrically charged particles surrounding the entire sphere. The 5 large moons of Uranus are all made up of water ice with perhaps hot, rocky cores. They are named Ariel, Umbriel, Titania, Oberon, and last, but certainly not least, Miranda. Most of these moons show signs of recent geologic activity. Of the large moons, Miranda is by far the most remarkable. Its surface looks as if someone took a cosmic-sized broom and swept across its face.
Then there's Neptune. Orbiting 30 times farther from the sun than the Earth, Neptune is most certainly a very cold place. And very little was known about the 8th planet until recently. With the Voyager's encounter, we've learned Neptune's atmosphere is surprisingly active.
This atmosphere, like Jupiter's, has a multitude of bright and dark bands. Bright white and dark black clouds take shape and then dissipate in the upper atmosphere, just as they do on Jupiter. And, once again like Jupiter, Neptune harbors a huge storm in the atmosphere. The scientists who found it appropriately dubbed it the Great Dark Spot. Above and below this storm, small white clouds dash around at over 1,000 miles an hour. Some of them go in the same direction as the dark spot, and others move the opposite way. Scientists call them scooters. Neptune is about the same size as Uranus, but it's not tipped on its side. Its orbital axis is a relatively average 28 degrees. The analysis of Neptune has shown that it's made up of a solid core of rock and water ice. But there appears to be evidence of methane ice as well, creating a chilly surface temperature of some 200 degrees below zero.
Nonetheless, the measured radiation from the planet is greater than that which can be accounted for by the meager amount of sunlight that strikes it. Like Jupiter and Saturn, Neptune is mysteriously giving off more heat than it's receiving from the sun.
Neptune has 2 significant moons. Triton is about 2,000 miles in diameter and has a methane ice coating. Nereid is barely larger than an asteroid at 185 miles in diameter. Triton's orbit is completely opposite that of the rotation of Neptune, so it's unlikely that the two formed together out of the solar nebula. Scientists think Neptune captured this moon later. During part of its orbit, Triton passes very close to the planet's surface, and its gravity raises tremendous waves of liquid methane. These moon and their gravity tugs at it. This slows the satellite, causing it to come ever closer to the surface. One day, Triton will pass too close. Neptune's gravity will tear the satellite apart and create a new ring system around the planet.
The outermost planet of the solar system is Pluto. Because of its small size, 1,400 miles, Pluto's status as a planet has been a subject of debate. It's only about half the size of our moon, and most of that is made up of methane ice with a little rock thrown in for good measure. Pluto does have a satellite, Charon, so it has managed to hold its rank as a planet so far.
As I made that picture, it would probably be like a cratered surface on Pluto due to the frozen methane frost on the surface, making it rather highly reflective.
People on Earth will experience nearly 2.5 centuries during the time it takes Pluto to go around the sun once. In other words, Pluto's year is about 250 times longer than a year on Earth. Pluto's average distance from the sun is 3.7 billion miles, and that makes it the 9th planet. But its orbit is very lopsided. Today, it's only 2.8 billion miles from the sun. For the next few years, it'll be closer to the sun than Neptune is. Besides swinging way out and back in, Pluto's orbit tilts at an angle different from all the other planets. Its satellite, Charon, was unknown until 1978. It's about 475 miles in diameter and orbits Pluto once every 6.4 days. This matches exactly the rotation of its parent. To an observer on Pluto, the moon would always be in the same spot in the sky. The sun, seen from the surface, would shine dimly like a distant star. Pluto is an appropriate name for the 9th planet. It's the domain of the god of the underworld, the god of an ice-cold hell. Pluto and Charon will never be high on our list of planets to explore. They're simply too far away and much too cold for us. So where do we go from here? The planets in our solar system may be our closest neighbors, but they're still very far away. To give you an idea how far away some of them are, think about this. Light travels at 186,000 miles per second. The radio signals sent by the Voyager spacecraft travel at the speed of light. So even traveling at the speed of light, it took Voyager's signal 4 hours to reach the Earth from Neptune. To look at it another way, were you able to drive your car at 100 miles an hour for 24 hours a day, 365 days a year on a highway that led to Pluto, if there was one, it would take 4,189 years to get there. The distances between us and our planetary cousins are truly astounding. But thanks to our technology, they are definitely within our reach. We will have to begin our journeys to the stars by first exploring and then learning to live on the worlds of fire and ice. Have you ever walked out under such a nighttime sky as this, looked up at the millions of stars, and wondered where it all came from? Most of us have, at one time or another. It's one of the most common and profound of human experiences. Many of the secrets of the universe are discovered here, on Mauna Kea, in Hawaii. We like to know the reasons why things are the way they are, and generally, the explanation we like is the one that makes the most sense to us. The simpler it is, the more clarity the answer has, the more we like it. So far as we know, we're the only species that has developed a system for answering some of these questions. The human invention called science. In the thousands of years that this invention's been around, we've come to know the world around us much more intimately. Each day we see a little more clearly into the tiny world of the atom and the giant complexities of Earth's ecosystems. We're even beginning to unravel the miracle of life itself. But science has also taken our understanding far beyond the bounds of our small blue planet. We're starting to understand the really perplexing questions that have bothered us since we first looked toward the heavens. Questions that we once thought best left to the philosophers and holy men. Questions like, where did the universe come from? How long has it been here? And ultimately, when did time begin? But the answers
can be even more perplexing, for as we will see, time itself began with the universe.
In Europe until the 16th century, people measured time with the fluid vagueness of the sundial, or the hourglass. For an explanation of the ultimate beginning, they looked to the Old Testament, and no further. The earth left
The most accurate answer to questions such as these. It is simple, it is elegant, and more so. It closely matches the dominant scientific theory today. What St. Augustine stated was this: there was no time and no space before the beginning. Now, this is a concept that admittedly boggles the mind, but we have come to hold the view because it best explains what is observed in distant space, billions of light years away.
The idea started with the work of astronomer Edwin Hubble. In the 1920s, Hubble began observing distant galaxies, trying to determine which way they were moving. At that time, many astronomers thought the universe was infinite and unchanging. In such a steady-state universe, as they called it, galaxies should be moving randomly throughout the universe. So equal numbers of galaxies should be moving toward the Earth as away from it. Astonishingly, Hubble discovered that all the distant galaxies he observed were flying away from us and from each other. And the further out they were, the faster they seemed to be going. Before long, scientists combined Hubble's observations with the fascinating new theories of a young man named Albert Einstein, changing our view of the universe forever. Because if all the galaxies in the universe, scientists ran galactic cluster motion in reverse and determined that everything was in one place some 15 billion years ago. From this unimaginably small point exploded forth everything that makes up the universe. This was the Big Bang, and it was also when time began.
Now, it is, admittedly, a difficult concept to imagine, time having a beginning. We are creatures that exist in time. We know that our parents lived lives before us and their parents before them, so we feel deeply in our bones that there must have been something happening before the beginning of time. But if something happened before the beginning, then whatever it was becomes the beginning itself. So we have two choices, neither of which satisfies our desire for completeness. Either time has gone on forever, or it has a beginning.
Scientists believe that time began with the universe because time and space are inseparably linked. The one cannot exist without the other. You see, the essence of time is change, and change is expressed as movement through space. You can see this by looking at a clock on the wall. The hands of the clock move along the course of the dial. The Earth rotates in space once every day, and around the sun once every year. Movement through space is the essence of time.
The movement may only be small, like the second hand on this watch, but it is still movement. When we talk about the Big Bang, we are talking about an instant when all the space of the universe was constricted to a size trillions upon trillions of times smaller than the nucleus of an atom.
Without room for movement, there could be no time. When the universe was so small that it had no size, no dimension, time stood still. The exploding out created space and time and the universe we see today.
But before we explain what most scientists feel happened at the beginning of the universe, we want to clear up some misunderstandings regarding the Big Bang. Firstly, it was not some incredibly dense piece of matter which fragmented and exploded outward into a vast, infinite space. It was pure energy, a substance as exotic as any ever imagined in science fiction. All matter, as we know it, came from this pure energy.
You see, Einstein's famous equation for converting mass to energy, E equals mc squared, works both ways. We've used it to turn a very tiny bit of mass into a whole lot of energy, a force that can light up our cities or blow them apart. But we've also learned to create a very small amount of mass from huge amounts of energy in laboratories. Not much, but enough to prove it can be done. Secondly, the Big Bang did not explode into space like a bomb going off in a room. Space did not exist at the beginning of time.
The idea of the Big Bang Theory is that the whole universe began at a certain instant about 15 billion years ago, and the universe itself expanded from an infinitesimal size. And what people often don't understand is there isn't an explosion where stuff is coming out into a wider space. It was space itself that was exploding and getting larger.
We'll return to the Practical Guide to the Universe on the Learning Channel. I'll return to the Practical Guide to the Universe on the Learning Channel. In the beginning, there was the force, the one force of which all things were made. Scientists suggesting this theory called this force quantum gravity. But what was its origin?
We really don't know. There's no way to tell. One kind of speculation is that quantum mechanics, which allows things to happen spontaneously, could create a whole universe spontaneously out of nothing. And if it could do that, maybe it could create many thousands or billions of universes all by themselves that we would not know anything about.
Whatever its source, the quantum gravity arose and began to form the universe. This single force contained what was necessary to create all the things we see in space and in the universe today. This infinitely small point of pure energy began to expand at the speed of light. This, then, was the start of the Big Bang. Once the universe began expanding, it cooled a little, just enough to produce a phase change. We're all familiar with the phase changes in matter. Water goes through phase changes as it cools from steam to form liquid water, and then again to form ice. Something very similar happened with quantum gravity. It went through more than one phase change. The first phase change caused the original energy to split into two forces, gravity and something called the unified force. And this happened instantly. That is, 10 to the minus 43 seconds after the universe began. This number, 10 to the minus 43 seconds, we are not talking about time in any ordinary sense. The number 10 to the minus 43 divides a second into extremely tiny bits of time that are small beyond human understanding. 1 second is a small interval. We can barely grasp it before it is gone. The term 10 to the minus 2 seconds splits that brief measure into 100 parts. A stopwatch for racing uses hundredths of a second. A nanosecond, 10 to the minus 9 second, cuts a second into a billion parts. A billionth of a second. To us it's instantaneous, but we still must divide it more finely. Cutting a nanosecond by another billion, we get 10 to the minus 18 seconds. Still a long way to go to reach 10 to the minus 43. But we're already dividing a single second into more divisions than there are numbers of seconds since the universe began. We must multiply that number by 1 trillion to reach 10 to the minus 30, and again by 10 trillion to reach 10 to the minus 43. So, as you can see, 10 to the minus 43 seconds is a very short time. The dual force cosmos didn't last long. By 10 to the minus 35 seconds, the universe had expanded and cooled enough to cause another breakup in the primary forces. The short-lived unified force split again, triggering a wild expansion of our then tiny universe. Quicker than the speed of light, it grew from a size smaller than an atom to the size of a softball. This faster-than-light growth of the universe was possible because space itself was stretching, not because things were moving through space at impossible speeds. It was only after this inflation that some sort of matter appeared that we can create in a lab. Tiny building blocks of matter far smaller than atoms called quarks. At 1 trillionth of a second, one of the three forces of the universe broke up yet again, creating the more familiar four forces of present-day physics: gravity, electromagnetism, the strong nuclear force, which holds atoms together, and the weak nuclear force which causes radioactive elements to decay. At this stage, the universe was nearly 2 miles across, and the temperature had cooled down to only about 1 trillion degrees. At a second old, the universe was still less than 200,000 miles across. It would have fit easily between the Earth and the Moon. The average temperature had dropped to 100 million degrees, still hotter than the inside of an average star. 1 minute after the beginning, if we use our solar system for scale, the whole universe, centered at the Sun, would reach 1/3 the distance to the first planet, Mercury. It took 100,000 years for the universe to grow large enough and therefore cool enough for atoms to appear. By then, the reign of energy came to a close, leaving matter to dominate the universe. Atoms appeared in 2 simple forms. Hydrogen atoms made up 90% of the matter that precipitated out of the energy. Helium, the next simplest, made up the rest. These 2 gases filled every cubic foot of the cosmos from one side to the other. Finally, the universe began taking on the mind-boggling proportions we've come to associate with it. Quickly, it reached a size that would envelop our entire galaxy. Virtually all the matter in the present-day universe had been created. The average temperature of space dropped down past 3,000 degrees. During its early phase, the explosion of the universe had been a dark affair, because light did not exist. But the creation of atoms liberated large amounts of light energy, called photons. This meant that the universe, which had been hot and dark, suddenly shined. Huge quantities of blinding white light filled every corner. Any features emerging in the still young universe would have been invisible because everything glowed with the same brilliant heat. But the time of light passed too, and space took on the blackness that we're familiar with today. It was an immensely colder cosmos than it had been. One force had given way to 4. Matter dominated the universe, and slowly, matter began to reform and change. In this still young universe full of new atoms, 2 forces began to shape and mold the hydrogen and helium that was present. COBE, the Cosmic Background Explorer, is one of the great satellite observatories. It has detected in the deepest part of space slightly greater densities of gas, places where gravity could begin shaping galaxies.
In all probability, galaxies formed before stars, that there were huge concentrations of material resulting from what COBE saw in their recent observations, the fluctuations in the density of material that came out of the Big Bang itself, formed little islands in the sea of radiation and matter that originated from the Big Bang. And these islands of material gradually condensed into galaxies, which were huge clouds, and within those clouds, stars formed from smaller parts of the clouds. So what we call a galaxy is a collection of stars and probably formed more or less as a unit.
In the regions where galaxies form, gravity and electromagnetic forces cause masses of gas to accumulate. Spheres of gas emerged. The atoms within them, crushed by gravity, grew hot. The densest parts reached temperatures of 15 million degrees. The universe witnessed the birth of its first stars. We'll return to the Practical Guide to the Universe on the Learning Channel. To the Practical Guide to the Universe on the Learning Channel. Today, billions of years later, creatures evolved from the matter created in the early universe, look outward from their small satellite orbiting a rather insignificant sun, and ponder the meaning of it all. The universe continues its expansion, and the remnants of the Big Bang glow faintly in the celestial background, awaiting mankind's analysis. With ever more sophisticated observatories like the Cosmic Background Explorer, we're getting closer to discovering the true beginnings of the universe. But what can we say about its end? Will the universal expansion set in motion by the Big Bang continue forever? Or will all things fall back together in what's called the Big Crunch?
You know, there is an idea that the universe is slowing down. And then instead of one of these types of accordion on you, it slows down and stops and then comes back together. And of course, when it comes back in, then you have the great collapse. You know, it's an expanding universe.
We're uncertain about the end of the universe because we really don't know how much total matter there is in the cosmos. If we count just the stars, we know there's not enough matter to cause it to collapse. If that's true, the universe will go on expanding forever. But stars aren't the only matter in the universe. Planets, moons, comets, asteroids, and dust count too. Optical telescopes don't show these well. With infrared telescopes placed in orbit, we're able to see even these kinds. Still not enough to stop the expansion.
In astronomy, currently, there is a search for an elusive substance called dark matter. This is an unknown material, or possibly numerous black holes that might be present throughout the universe. This dark matter is called dark because it emits no light, which makes it invisible in space.
The Big Bang theory currently believed to be most accurate predicts the existence of dark matter, and the behavior of some galaxies also indicates its presence. These galaxies spin so rapidly they should fly apart, but they're held together by a huge gravity field, which tells us that there's more matter in these galaxies than meets the eye. Dark matter? Possibly. If there's enough dark matter in the universe to slow and then halt expansion, then all the galaxies in the universe will someday begin to drift back towards each other. They'll eventually crash and compress back down to that single point of pure energy, perhaps to begin the cycle all over again. But if the universe continues to expand, it's still doomed to destruction. Over billions of years, all the hydrogen used by stars to produce their bright light will burn off. One by one, the stars in the sky will disappear, leaving a cold, lifeless universe behind.
For us humans, the question of whether the universe will continue to expand or finally contract is of no immediate consequence. In either case, it'll be billions of years before the end comes, and by then even our sun will be long dead. So for us as individuals, it will matter little, but will the race survive? Can humans evolve and become so smart that we can outwit the end of the universe? Another question to ponder. Perhaps from the small beginnings of the universe, the greatest force has emerged just in the last 50,000 years. It is the force of the human mind and imagination.